Welcome, future pilots. If you're a PPL student gearing up for that ground exam, you're in the right spot. Let's be real, aerodynamics theory can feel pretty overwhelming when you just want to figure out how to keep a Cessna in the sky. So let's cut the fluff. Today, we're jumping right into exactly what you need to know to absolutely ace the aerodynamics section of your exam. No heavy jargon, just the core principles that literally make flight possible. Let's get into it.
Okay, so right off the bat, let's tackle this huge debate. If you've spent, any time on aviation forums or chatting with veteran pilots, you've definitely heard it. Who's actually flying the plane? Is it Isaac Newton and his physical laws of motion pushing it up, or is it Daniel Bernoulli with his fluid pressure principles? It's a classic trick question, and it trips up a ton of students. To nail this on your exam, we really need to unpack what both of these legends brought to the table.
Let's kick things off with Sir Isaac Newton. His basic laws of motion are the absolute foundation for, well, anything moving in our universe, airplanes included. The first law, inertia, meaning your aircraft is going to just sit there on the ramp until a force strong enough to overcome its mass kicks in. The second law, force equals mass times acceleration, tells us exactly how much thrust we need to get moving. But for your exam, highlight the third law. That's the real star here. For every action, there's an equal and opposite reaction. To move forward, the prop pushes air backward. To go upward, your wing absolutely has to push air downward.
The easiest way to visualize this? The classic car window metaphor. Come on, we've all done it. You're cruising down the highway, you stick your hand out the window, and you angle the front of your hand up. Bam! Your hand gets forced upward instantly. You're deflecting that oncoming massive air downward, which creates this Newtonian equal and opposite reaction that physically shoves your hand, or in our case, a wing, up into the air. This concept of flow turning through deflection is a massive, massive piece of the lift puzzle.
But hey, to truly grasp how a wing manipulates the air, we gotta look at the air itself. Air isn't just empty space, right? In aerodynamics, we actually treat air as a fluid, and fluids have these specific properties. The absolute most important one, viscosity. Basically, viscosity is just the molecular tendency of fluids to stick to each other and to surfaces. It's what causes them to resist flowing smoothly.
Picture this. You pour thick engine oil and regular water down a ramp. The oil has super high viscosity, right? So it resists moving, it moves really slowly, and it clings to the ramp. Water flows way easier. Now, air has a very low viscosity compared to liquids, but, and write this down for your exam, it still has some viscosity. It definitely still resists flow, and it really wants to stick to whatever surface it's moving over.
And that brings us right to friction. Here's the kicker. As this viscous air flows over your wing, it gets slowed down by surface friction. You might look at a super polished aircraft wing and think, wow, that's perfectly smooth. But if you slap that aircraft-grade aluminum under a microscope at, say, 1,500 times magnification, it literally looks like a rugged mountain range. All those microscopic bumps grab onto the air molecules. The air right next to the metal drags to a near halt, which then slows the air just above it, creating this incredibly complex interaction between the wing and the sky.
This exact interaction sets up a super cool phenomenon called the Magnus effect. Imagine taking a cylinder and spinning it while moving it through the air. The friction we just talked about drags the air right along with the spin. That makes the air move way faster over the top of the cylinder and slower on the bottom. The result? A perfectly measurable upward force. It practically proves that if you change the velocity of air over a surface, you generate lift.
Now hold on to that idea of speeding up air, and let's look at a Venturi tube. A Venturi tube is basically just a pipe that starts wide, narrows down in the middle at what we call a throat, and then widens back out. When air gets forced through that skinny, constricted section, it literally has to speed up to push the same volume through the smaller gap. And when it speeds up, something pretty magical happens. The internal pressure of that fluid drops.
Enter Daniel Bernoulli. About a half-century after Newton, Bernoulli mathematically proved this exact principle. Bernoulli's principle simply states that as the velocity of a moving fluid goes up, the pressure inside that fluid goes down. It's a high-speed, low-pressure reality. And honestly, this is the master key to understanding how we shape modern aerofoils to completely manipulate the sky.
Let's put this all together on a real airplane wing. If you slice a wing right down the middle, you'll notice it looks an awful lot like a half Venturi tube. As the wing shoves through the air, that curved top surface forces the air to speed up. Thanks to our guy Bernoulli, we know this faster velocity drops the pressure above the wing. Meanwhile, down on the relatively flat bottom surface, the air is moving slower, which builds a positive, higher pressure. This pressure differential means the high pressure below literally pushes the aircraft upward into the low pressure vacuum up top. Pretty wild, right?
Now, for the exam, you absolutely have to know the anatomy of the wing that makes this happen. First up, the chord line. Please don't overcomplicate this one. The chord light is just a perfectly straight reference line drawn from the very front edge of the wing, the leading edge, to the very back, the trailing edge, just straight as an arrow.
The mean camber line, on the other hand, is a slightly different story. You draw this line from the leading edge to the trailing edge, but you keep it perfectly equidistant from the upper and lower surfaces at all times. Since the top of a standard wing usually has more curve to it than the flatter bottom, the mean camber line actually bends. It follows the true physical curve of the wing. Memorize the difference between these two lines, guys. It is guaranteed easy points on test day.
Also pay close attention to stagnation points. When your wing slams into the oncoming air, there's one specific spot right on the leading edge where the airflow hits the metal and literally stops moving, just for a fraction of a millisecond before it decides to split and go either over or under the wing. We call that the front stagnation point. And yep, you guessed it, there's also a rear stagnation point where those two airstreams meet back up at the trailing edge.
Okay, so back to our big opening question. Who's flying the plane? Is it Newtonian deflection, or is it the Bernoulli pressure differential? Well, the grand reveal for your ground exam is it's both. Yep, both of these forces are completely active anytime an aerofoil generates lift. You need that physical, downward deflection of air and the beautifully engineered pressure drop over the curve to lift a multi-thousand-pound machine off the runway safely. It really is the ultimate partnership of physics. Now, sitting in the cockpit, you're not just along for the ride. You are controlling the aircraft. And you do that mostly by altering your angle of attack. When you change your angle of attack, you actually shift something called the center of pressure, or the CP. Think of the CP as the single theoretical point right on the chord line where all of that lifting force is concentrated. Mock this next bit into your memory right now because it is a classic exam question. When you're cruising fast and level at a low angle of attack, that center of pressure moves aft, so backward, towards the trailing edge. But the second you pull that yoke back and pitch the nose up into a high angle of attack, that center of pressure aggressively shifts forward, toward the leading edge. Aircraft designers actually have to build heavily reinforced wing structures just to handle these massive shifting air loads. Let's follow that air all the way to the back. When the airflow from the top and bottom reunite at that rear stagnation point we talked about, the flow is pointed downward and backward. We call this downwash. And honestly, this downwash is the final, essential Newtonian reaction. The air is forced down, and the equal and opposite reaction gives you that beautiful upward push of lift. Up until now, we've only been looking at a clean 2D slice of the wing, but airplanes fly in a 3D world, right? So, what happens at the very end of your wing? You know, out where the aluminum ends and the open sky begins.
Well, nature absolutely hates an imbalance. That high-pressure air clustered underneath your wing is constantly trying to sneak around the wingtip to reach that low-pressure vacuum sitting on top. This violent little escape route creates a spiraling, rotating tornado of air trailing right off your wingtips. You've probably heard of it, the wingtip vortex.
And these vortices aren't just cool to look at when it's foggy out. They're actually a huge problem. They create a downward flow that actively robs you of your total lift. To fight back, engineers got clever. They install winglets. You know those sleek upward bends at the ends of modern wings? Those act like physical dams, blocking the high-pressure air from spilling over. They also taper the aerofoil tip down to a narrow point, which minimizes the pressure difference right there at the very edge. So, bringing this all together, a wing isn't just a hunk of metal, and it sure isn't magic. It's a deliberate, calculated engineering marvel. It perfectly bends the universe's basic rules: friction, viscosity, pressure drops, and equal and opposite reactions, totally to your advantage. Wrapping your head around how all these forces weave together won't just get you a passing grade, it's going to make you a far safer, more intuitive pilot.
I really hope this explainer totally demystifies these aerodynamic concepts for you and gives you the confidence to just crush your ground exam. Hey, if you found this breakdown helpful, please hit that like button and subscribe for more PPL Ground School explainers. I'm going to leave you with this final thought today. Now that you know exactly how insanely complex the air flowing over your wing is, what other invisible forces of flight might you be taking for granted? Stay curious, study hard, and we'll see you in the skies.